System means processor is present here, because this processor, memory is there, memory interface is there, plus on chip cache memory is also present. We can connect external memory, DDR memory, okay, right. So plus FPGA fabrics, all interfaces, processing system, as well as the memory is present. That's why we call it as this is SoC, system on a chip. Complete system we can implement on this FPGA. The internal the details of that block diagram. So application processor unit, memory interface, IO peripheral interface, interconnect. That is about PS processing system. Program logic is PL, PS and PL. Okay. So this is internal blocks of the processor core. That ARM processor internal blocks. Two dual core ARM processors are there. No? Each internal there is a arithmetic logic unit, ARM Cortex A and CPU. This is ARM processor core. Plus floating point unit, that is a floating point arithmetic operations also we can execute on this processor core. Then memory management unit, we can connect this processor core with external memory, DDR type of memory. So, okay, DDR means 4 GB or 2 GB, 8 GB memory we can interface. Then cache memory, on chip cache memory also present here. 32 KB instruction cache and 32 KB data cache memory. Okay. So that type of processor cores dual, two are there in this. Plus L2 cache memory also, 512 KB L2 cache memory, L1 cache memory and L2 cache memory. And then also on chip some memory, small memory is also present, that is a 256K SRAM memory is also present. Okay. And 8 DMA channels, you studied DMA, right? So DMA channels, 8 DMA channels also present. Okay, same thing it is again, once again it is shown here. So if you see APU, each APU internally contains ARM Cortex A9 CPU, Neon unit, floating point unit, memory management unit, L1 cache. Snoop controller is a cache related. L2 cache, system level control registers, accelerator coherency port, on chip SRAM, DMA controller, general interrupt controller, timers. So the pins, dedicated pins, 54 dedicated pins, because these pins are shared between multiple functions. So but external is concerned MIO, so 54 dedicated pins are there, but these are shared across multiple functions. Okay. It can be shared for DMA or USB or maybe SD card or maybe, so the different functionality is there in this. Okay. These pins are shared across multiple operations, multiple functions. Input output peripherals, 2 gigabit Ethernet controllers, 2 USB controllers, 2 SPI controllers, 2 SD card controllers, 2 CAN, 2 I2C, 2 UART, 4 32-bit GPIOs, static memory interfaces, NAND and NOR SPI, quad SPI flash and trace ports. These are all features of this IO processor interfaces for the input output peripherals. Memory is concerned, DDR memory controller, quad SPI controller and static memory controller. These 3 memory controllers are going to present inside the FPGA fabric. This is a DDR memory controller block diagram internally, external DDR memory interfacing. Interconnects are actually internal FPGA fabric to CPU processor core, the interconnections is also there. FPGA fabric to the processor core interconnect. That interconnect is primarily mechanism for data communication. Interconnect located within the PS comprises of multiple switches to connect system resources using AXI. AXI point-to-point channels for communicating address, data and response transaction between master and slave clients. So, what is AXI? AXI is a part of ARM AMBA 3.0 interconnect. Okay. So, if you see interconnect features are, the interconnect is based on AXI high performance data path switches, Snoop control unit, L2 cache controller, and interconnect switches based on ARM NIC 301. So, central interconnect, master interconnect for slave peripherals, slave interconnect for master peripherals, memory interconnect, OCM on chip memory interconnect, AHB and APB bridges. So, this is your AXI interconnect. So, this is the AMBA interface, that AMBA is advanced microcontroller bus architecture. Okay. This is for interconnecting a FPGA fabric with processor core. So, in this APB, AHB, AXI, so this is sub interfaces, or maybe these are actually AMBA 3.0, this is in standard 3.0. So, in that these are the bus interfaces basically from AMBA bus architecture. AMBA bus architecture internal sub interfaces. Okay. So, peripheral bus, high performance bus and AXI bus. AXI is here advanced extensible interface. This is a Xilinx FPGA, mainly for Xilinx logic interconnection purpose, this AXI used. Xilinx FPGA fabric interconnection purpose only this AXI is developed. But this is developed by ARM organization only, AXI, AMBA bus. But HB, APB, these are all part of the AMBA only. Yeah, just see this, and quickly I close this. AXI interconnects AMBA, if you see APB, AHB, AXI, ATB. So, in this AXI again 3 categories. AXI is, what is AXI? AXI is, I told you know, this is advanced extensible interface. Advanced, this APB is advanced peripheral bus or AMBA advanced peripheral bus. What is APB? Peripheral bus only. A for advanced we can use, or AMBA we can use. A is AMBA actually. This is AMBA, from the AMBA only this has derived, these 3 bus interfaces. Peripheral bus, AMBA, peripheral bus, AMBA high performance bus. So, but here advanced extensible interface, that means you can also use A, advanced peripheral bus, advanced high performance bus, advanced extensible interface. Extensible. This advanced extensible interface AXI bus, this bus is mainly for interfacing FPGA fabric with the processor core. So, this AXI again divided into subcategories. AXI 4 memory map, AXI 4 stream, AXI 4 light. These are the 3 subcategories of AXI, that is AMBA 4.0. This is AMBA 3.0 is these categories APB, AHB, AXI. Okay. So, if you see the difference, AXI 4 memory map full, traditional address data burst, single address multiple data. Burst transfer operations, if you want burst transfer, then you have to use AXI 4 memory map interface. This is a traditional address data burst transfer, single address multiple data. Burst type of data, burst data is burst data means multiple data, multi data, single address, same single address, multi data we can transmit, DMA transfers. So, this similar to this here it is again PLB V46 and PCI. Streaming AXI 4 stream, this is one more subcategory of AXI 4 streaming. This is data only, there is no address, continuous transmission of the data, streaming. Data only and burst, like DSP interface, FIFO, FSL, local link. So, streaming is data only or burst transfers also we can use, data only. The light transfers are AXI light, one more is AXI 4 light. This is a traditional address data, no burst transfer is allowed here. It is only single address, single data only we are going to transfer in AXI 4 light. Okay, you can use AXI 4 light or AXI 4 full or streaming. Any one of these three interfaces you can use to communicate with the processor core inside the FPGA with FPGA fabric. Okay. So, each Zinc 7000 device contains CMPS with PL and IO resources vary between the devices. There are different types of 7000 series devices, Zinc devices. So, 7010, 7015, 7020, these are a dual core, whereas 7007, 7012, 7014, those are one single core only. The PL based is the PL based Arctic 7 series FPGA logic. PL is Arctic 7 only, all FPGAs Arctic FPGA fabric. Then coming to 7030, 7035, 7045, 7100, but here only PL is varied. PL is Kintex based. PL is Kintex based FPGA fabric remaining. So, but the device side, processor side remains same. So, PS and PL can tightly or loosely coupled using multiple interfaces and other signals that have combined a total of 3000 connections. PL can be a separate power domain from the PS, saves power. So, different power up operations also possible, different power modes. Yeah. So, configurable logical block, the PL side, 6 input lookup table, that is why morning we have discussed lookup table size. So, this all these FPGAs 6 input LUT, memory capability within the LUT. Okay, each LUT if you want to convert into memory, it is possible, memory capability. Then register and shift register functionality, that means each LUT we can also convert into a shift register. If you want to, you can use as a shift register also, that possibility is also there. You can convert that LUT into a shift register. And cascadable adders. So, for example, ripple carry adder type of adder, suppose if you want to implement 32-bit adder, 64-bit adder. So, that cascading type logic is automation, automatically it will be cascaded. Okay. Cascadable adders also we can create with the help of the LUTs. But memory is concerned 32 KB block RAM, 32 KB, KB is kilobytes here, 32 KB kilobytes of block RAMs. How many are there? We do not know. How many are there in this? Not given. Dual port, okay, and up to 72-bit wide. That means we can increase the width also, memory block. Memory width also we can increase. Width is memory width 8-bit. If we connect in parallel, we can increase the width. If you connect in serial, increase the size. Configurable as a dual 18 KB. So, this is 32 KB, no? So, configurable as a dual 18 KB. We can configure that into 18 KB, dual 18 KB also. We can convert that into two 18 KBs. Or you can increase the 36 to 72 KB like that, we can also increase. Programmable FIFO logic, we can also convert into FIFO. We can use as a FIFO. Built-in error correction and circuitry, that is memory error correction circuitry also built in this. Yeah, DSP slice. DSP slice, we have seen DSP slice morning. So, here 25 by 18 2's complement multiplier accumulator, high resolution, 48-bit multiplier accumulator, 25 by 8 2's complement multiplier and accumulator, high resolution, 48-bit by 48-bit multiplier and accumulator also possible. 25 by 18 2's complement multiplier accumulator or 48-bit multiplier and accumulator. We can configure that DSP. Power saving 25-bit pre-added to optimize symmetrical filter applications. 25-bit pre-adder. Then advanced features like optional pipelining, optional ALU and dedicated buses for cascading. These are the some of the features of the DSP. Clock management, high speed buffers, routing of low skew clock distribution. Clock will be actually not uh, clock is actually clock managing circuit is going to present, that will distribute the clock across all CLBs in a tree fashion. So equal length will be maintained, the clock skew will be eliminated. So low jitter clock generation, jitter filtering, that clock management will take care of this. Frequency synthesis and phase shifting, configurable IOs, input output pins, blocks, high performance select IO technology, high performance decoupling capacitors within the package for enhanced signal integrity. So this is IOs, about input output pins, and a digitally controlled impedance that can be three stated for lowest power or high speed IO operation. High range IO supporting 1.2 volts to 3.3 volts, high performance IO support 1.2 volts to 1.8 volts. That is the IO technology we can use for higher range or high performance. Low power serial transceivers, the serial transceivers, high performance transceivers, low power transceivers are in these devices, low power serial transceivers. High power transceivers are capable up to 12.5 gigabits per second GTX in these devices 303545, but ours is 7020, it is not comes under this category. Okay. High performance transceiver capable up to 6.25 in 7012, 7015. Low power mode optimized for chip to chip interfaces. Okay, 7020, I think serial interface is not there. PCI Express, integrated interface block for PCI Express designs. PCI Express is serial PCI interface. PCI is a parallel interface, PCI bus, but PCI Express is a serial PCI interface logic. Latest laptops all will contain only PCI Express interface only. But compatible with PCI Express base specifications and supports generation 2 5 gigabits per second. Advanced configuration options, advanced error reporting and end-to-end CRC, advanced error reporting and eCRC features. These are important features for the this FPGA fabric, the Zinc 7000 FPGA. Okay. Processor design చెప్పాలా లేకుంటే processor design అంటే it will take almost ఒక 1 hour 1.5 hour ఇదే అవుతుంది. module name is automatically will come. Next is here the simple multiplier module code. So input output. So here 8-bit input, 8-bit input A and B 8-bit input, and then the product. So then product is equal to A into B. Product is A into B. This symbol A into B. Directly a symbol used. We are not written any code for multiplication algorithm. Directly symbol used. Arithmetic library component that is directly used. So A into B. That's also a simple program. That will be 8-bit multiplier. Right. So then after that, this is your source code. Okay. So to test this source code, we have to do simulation, simulate and verify. For this simulation, we have to create one test bench. We have to create a test bench code. The test bench code again, the module test bench, and this is the register names. Same that input names are there as this. The same names you have to type here. Test A, B 8 bits each. Then this product is again 16 bits. Then this is the instantiation of the module, multiplier module instantiation in the test bench. Okay. So this dot A, dot B, the product is the instantiation of the test code. Sorry, the component under test. Then this was the test input generation, the test cases. These are all test cases. We are giving test input of first is we are giving 5, decimal 5, and B is decimal 10. A is decimal 5 and B is decimal 10. Test input, and after 10 time units, 10 nanoseconds delay, then A, B we are giving again same input again. Different input. Okay, 5 and 20. Then third case is 100, 200. And fourth case is 255 and 255. These are the 4 test cases here. So for every test case input, there is a delay of 10 nanoseconds. 10 nanoseconds delay. This is about test bench. Then this is for monitoring display. For example, time. So okay, it will be display what is the A value, B value, and product value. Will be displayed like a printf type. Okay, then the next step is you have to run simulation. Okay, so test simulation, test bench, you have to select and run favorite simulation. So here simulation and synthesis design now. So here this side you have to select the simulation operation there, that you have to click, then it will run the behavioral simulation. So then you are going to get waveforms like this. Okay, this is only one case as shown, last case 255 by 255 multiplication. This is the result. This is only up to this one is simulation, source creation and simulation, test bench creation. First is product creation, the next is source file creation, and test bench side creation, test bench, and testing of that source file. So simulation. So once you satisfy, once you get correct output, the next step is we can create a block design. We can implement this on the board also. Okay. So for that block design, we can go for block design. Block design, where you have to block design. Okay, you can select the block design here. So in the block design, this symbol, add the module to the block design, the sources panel. Locate your custom module under the design sources and right click on the module name and select add module to block design. So here the block design, already whatever you have created symbol, source file, that symbol is going to be created already in the sources panel. In the design sources. So that we have to add to this block design. The symbol is going to be created, that we can add to the block design. Schematic schematic symbol is going to be created for the multiplier source program. Okay, this is the symbol. Okay, that symbol we have to add in the block design. Block design is a schematic type of design, logical design. Okay, and here click on icon press add VIO. Double click on VIO, assign probe counts. Input is 1, output is 2. Input probe 1 and output probe 2. This is VIO. VIO. Okay, because here 2 inputs are there, 1 output is there. So we have to generate 2 inputs to this. 2 input ports are required, and this output we have to take. So VIO is virtual input output IP. So by using that, we can generate test inputs to this. Test inputs we can give to this VIO. So that's why, so 2 input ports, we are generating a 2 input port and 2 output ports, because 2 output ports are, you see, this is your multiplier. The multiplier, 8-bit multiplier. So 2 inputs are there here. This is 8 bits each. This is A and B. This is the product. This is the simple we have created. Product is, you see here, what is the product? Result. This is the multiplier symbol here created. To test this, after implementing and to test this, so when we are using one IP called VIO. This is VIO IP. Virtual input output IP. Okay. This, by using this IP, we can generate the test inputs. So what are the test inputs? 2 inputs are required. So that means here this output is connected as a input to this VIO. Output. That means output also you can monitor. Output we have to check. This is virtual input output testing of the. So that means the output we can monitor that. That's why this output of this you have to connect as input to this. And here it has to generate 2 outputs. That is A and B outputs. So these 2 outputs are will be connected to here. Here this will be connected. Outputs it is generating 2 outputs. Those 2 outputs will be connected. That means this VIO should generate 2 output ports. These are the 2 output ports and 1 input. Okay. So that's why here VIO count. Yeah. This is port count 1 and 2. This is input and this is output. 2 input. 1 input and 2 outputs. That IP, that we have to select here. Okay, after selecting this, then next is then the size of the port, each port size. That we have selected ports. These are the ports. What is the size of the port? Size of the port also you have to select, because here output is how many bits you are going to get? 16 bits. The port width, that is the output is multiplier source code output is 16 bit. But VIO it is input. So that means input port bit should be 16 bits. This is 16 bits. Probe. Okay, 16 bits. Similarly, output, the VIO output, 2 outputs are there from the VIO. Those are connecting to input of the source. What are the sizes of the outputs? VIO 8 bits each. So here 8 bits from output 0 to 8 bits. Okay. So this is the circuit. You see that is the connection whatever we have drawn. This is a similar connection is going to be you have to make in the block design. So simply we can draw that. Okay. So just take that VIO symbol from the IP. The design source is there. This VIO IP is there. That you just select and paste. And this also you can select and paste in the design menu. Then interconnect these two. Simply interconnecting this, you can get like this. One is VIO, one is multiplier. Okay, that one is multiplier, this is VIO. Okay, the next is up to this is sufficient, okay, for testing of the multiplier. You can do, because the DIO is used to generate the inputs. That about how it is going to generate, the generating inputs is through keypad only. The keypad you can enter the inputs. So 8-bit inputs were selected, right? So that if you just type this, automatically it will go to that DIO input that will be fed as the inputs. Okay? So here, these inputs, DIO will be, so because here DIO can be interacted, we can interact. This DIO inputs we can set through keyboard. Generating this, we are not writing any logic here. There is no logic in this. Simply the inputs, whatever outputs it is generating here, that is through keypad only. So your keyboard, you can type the numbers here. What are the numbers you want? That numbers will go as input to this. Okay? Then output, 16-bit, that output will be displayed on the screen. So through keypad interactions, this is actually the keypad. Virtual input output, that is, this is keyboard, and the display. Keyboard and display. Keyboard and display interface only. So through keyboard we can enter input, and output of this product we can display on the screen. But both will be displayed. Whatever you are typing, the keyboard also will be displayed. Okay? So, for testing of this logic, this DIO is sufficient. Simple. This is for not for simulation. Simulation we have already done through test bench. This is for after implementing on the board. Okay? This logic implementing on the board, we can test the logic by using this DIO. You can give the input and you can see the output. Okay? Simulation is simple. This is not required simulation. Simulation of this is not required. For simulation of this, what we read test bench here, right? Simple. This is multiplier. So only the test bench, from the test bench, this is test bench. Test bench is giving input, multiplier, and the output we are going to see on the screen. This is the output, 16-bit output. What is the waveforms? It's going to generate waveforms. Simulation waveforms, we can see the output. Different waveforms based on the test cases. This is for simulation. This is for implementation. Implementing on the board. And but this one is through, we can enter the values only. 8-bit values, 16-bit values, 30-bit, whatever the size, board size. Accordingly, you can enter the values, numbers. Integer number or floating point real numbers are connected. Okay? But this is an integer or 8-bit number. Or if you want waveforms also, if you want to see, like our simulation, here we have 4 different test cases, waveforms we are seeing. Sequential logic, this is a combination logic. It is a sequential logic, that is the waveforms. Okay? If you want to see the waveforms, then one more IP you have to use. That IP is IAV. That IAV is integrated logic analyzer. One more IP. So by using that IP, we can plot the waveforms also. Okay? So you see now. So ILA is a logic analyzer, you know, logic analyzer. Logic analyzer output waveforms like a CRO type. Logic analyzer is like a CRO, channels will be there. So using the channels, we can see the waveforms. CRO, 2 channels are there, 2 waveforms you can see. 3 channels, 3 waveforms. Okay? Similarly here, we have to see how many ports you have to observe. 2 input and 1 output. So that means 3 channels, 3 probes. 3 probes are required. So that ALA we can select 3 probes here. So selecting 3 probes. 3 channels, 2 input channels, 1 output channel. Okay? And same number of comparator outputs, then that's all. Okay? Then just we select. So probes here, number of probes. Then number of bits assigned in ILA. Number of bits also same number, like 8 bits. 8 bits inputs and 16-bit output. And number of comparators 1. So this is the final connection diagram. It's not properly visible here. schematic diagram, schematic problem is equal to light and the light. Okay, this is the multiplier. This one is multiplier, and this one is VIO, and this one is logic analyzer. Okay, multiplier, virtual input output, and logic analyzer. Logic analyzer, how it is connected? See, the multiplier inputs, same inputs are connected as one probe. Two inputs are there. Two inputs are just connected, and output also connected. Okay, this out the multiplier, two inputs and one output is there. Those three just connect to logic analyzer. That's all. Okay. So two inputs, this input is connected to logic analyzer. See, only logic analyzer can be used for testing without having VIO. Can we use VIO or can we use only logic analyzer for testing the circuit? Huh? Logic analyzer is for only just for seeing the waveforms, that's all. Okay, input output waveforms. So only logic analyzer not sufficient. Logic analyzer is just only output monitoring, like a CRO type. It is not generating test input. Test inputs are generated through VIO only. Right? Only logic analyzer not sufficient. Without logic analyzer also we can test by using VIO. Okay. So the next step is we have to assign pins. We have to assign the pins because this is FPGA core planning. Okay, in the core planning, the pins will be there. This FPGA internally contains some how many pins? 400 pins or 300 pins? Okay, so some around some 200 pins are there for this FPGA. We require how many pins? 8 in 8-bit inputs, 2 inputs are there. Okay. Then 16-bit output. Okay, 16-bit output to 8-bit input ports. So that means 32 pins. 32 pins plus 1 clock pin. So 33 pins we have to assign. Pins of the FPGA we have to assign. Okay. The pins of the FPGA can be selected package pins. So one is clock we are selecting here. Just clock. Clock is enough. Not required. Okay, this is internal operation. So if it is external connection to LEDs or switches, you have to assign the pins. This is inside FPGA. You need not assign any pins here because internally the ILA IP is